Hello there. I'm glad you've made it here. Let's take a moment to settle together in this quiet space, the kind where the air feels still, and even the smallest sound seems to float a little longer. Your breath has its own slow rhythm now, matching the calm of the room. Nothing to fix, nowhere to be, just the soft company of a voice and the gentle drift of thought. Tonight, we'll wander into one of the universe's quiet mysteries, the dark matter of space. It's everywhere, shaping galaxies, guiding stars, yet hiding completely from our eyes. We can't touch it or see it, but we feel its pull in everything that moves. Think of it as the universe's unseen hand, steady and patient, keeping the great cosmic dance in balance. As we drift deeper into the story, we'll follow the clues it leaves behind: curves of starlight, quiet bends in gravity, whispers written in the shape of galaxies. If this slow voyage feels like good company, a gentle like and a quiet subscribe help others find their way here too, only when it feels right, never in a hurry. For now, let your shoulders rest, let the dark hold you softly, and let's begin our night with the unseen. For almost a century, astronomers have been listening to a soft contradiction that hums beneath the glitter of the stars. Galaxies, those vast whirlpools of light, turn too fast for their own good. Their outer stars, fragile beads of brightness, should have been flung into the dark long ago, yet they remain, circling patiently, held by something no one can see. Whole clusters of galaxies drift through space, as if guided by invisible threads, graceful and sure, obeying laws that our eyes cannot measure. Every new observation whispered the same quiet message: there is more out there than light can ever tell us. If you could step back and look at the universe as a single vast tapestry, you would find that most of its weave lies hidden. The bright stars, the glowing clouds of gas, the swirls of nebulae, they are only the embroidery, the decoration on a much deeper fabric. The true material of the cosmos is silent, invisible, yet impossibly strong. It is what holds everything together, shaping galaxies, anchoring clusters, binding the universe in its gentle gravity. In the quiet years between the two world wars, when telescopes still turned by hand and the night sky was read through glass plates and patience, a Swiss astronomer named Fritz Zwicky began to notice something strange. He was studying the Coma Cluster, a gathering of thousands of galaxies drifting together through space, each one a glowing island made of billions of stars. Through his eyepiece, the cluster looked calm, serene, a lantern field scattered across infinity. But when he measured how those galaxies moved, the calm dissolved into confusion. They were racing too fast. According to the well-tested laws of gravity, there wasn't nearly enough visible matter to keep them bound. The galaxies should have flown apart like sparks scattered from a dying fire, yet they remained together, turning slowly within the same invisible embrace. Zwicky's numbers told a story that no one had asked to hear. The cluster appeared to weigh hundreds of times more than all its visible light could account for. Somewhere in the dark, there was mass without glow, something unseen, heavy, and necessary. He called it dunkel materia, dark matter. He did not mean the name to sound poetic. He simply needed words for the invisible glue that kept the universe from unraveling. His reasoning was simple enough to be undeniable. If something moves faster than expected, there must be extra gravity holding it in place. And gravity only obeys one law: the more mass, the stronger the pull. Zwicky's equations pointed toward an enormous hidden weight, silent but real. Few wanted to believe him, Zwicky was brilliant but bristly, sharp as the mountain air he loved, more comfortable with numbers than with niceties. Some dismissed him out of irritation, others out of disbelief. The universe, they said, could not possibly hide so much of itself. It was easier to assume his measurements were wrong than to imagine a cosmos filled with unseen substance. Yet, Zwicky's figures refused to fade. The coma cluster truly behaved as if it were swimming in a sea of invisible gravity. Picture it for a moment. You are floating high above that cluster, looking down through the black. Thousands of galaxies shimmer, below each one a whirl of light, each one drifting in slow motion. Between them, darkness stretches, seemingly empty, but that emptiness is not hollow. It carries the hidden weight that keeps the lanterns from drifting apart. If you could remove that unseen mass, the galaxies would scatter, their light thinning into the void until nothing remained but a faint echo of brightness. Zwicky's lonely calculations were the first small crack in the bright facade of the universe. He could not have known it, but behind every shimmering galaxy lay a shadowed architecture waiting to be revealed. The idea was too radical for its time, and for decades it slept quietly in the footnotes of astronomy. But the universe is patient. It keeps its truths until we are ready to listen. By the middle of the 20th century, new telescopes were watching the heavens with unprecedented precision. The night was still the same, but our instruments had become keener, our questions more daring. Among those who turned her gaze upward was Vera Rubin, a gentle and determined observer who preferred the company of stars to that of crowds. She loved the long rhythm of data, the quiet discipline of night work, the unhurried beauty of galaxies in motion. Rubin studied spiral galaxies, those elegant, swirling disks of starlight that seemed to drift like smoke frozen in midair. According to Newton's laws, stars near the center should orbit quickly, while those at the edge should move more slowly. The pull of gravity weakens with distance. That rule holds true from the planets in our own solar system to the stars in distant galaxies. Mercury whirls close to the sun in rapid circles, while faraway Neptune moves so leisurely that a single orbit takes more than a century and a half. The farther you are, the slower you go. That is how gravity is supposed to behave. But the galaxies Rubin observed did not listen. When she and her collaborator Kent Ford measured the speeds of stars at different distances from a galactic center, the pattern they expected never appeared. They traced the motions through the subtle shifts in starlight's color, the Doppler effect, and found that the stars on the outskirts moved just as fast as the ones near the heart. The graceful curve that should have dipped downward stayed stubbornly flat, stretching straight across the page like a defiant horizon. The galaxies, it seemed, were ignoring gravity's script. According to the visible mass alone, they should have torn themselves apart long ago. Yet they spun with quiet confidence, every star held in orbit by something unseen. To make sense of it, Rubin imagined that each galaxy must be surrounded by a vast, invisible halo, an envelope of dark matter extending far beyond the glow we can see. Picture a record player turning slowly in a dark room. The bright dots near the center spin swiftly, and you expect the faint ones near the edge to fall behind, but they don't. Even the dimmest lights keep pace, circling in time, as if the music itself insists on perfect rhythm. The galaxy is the record. The dark matter halo is the steady hand keeping time, inaudible but essential. Rubin's data spoke with the same clarity wherever she looked. Tiny dwarf galaxies, massive spirals, it made no difference. The same pattern returned, elegant and persistent. Flat rotation curves, swift outer stars, hidden mass. What began as an anomaly became a law of the universe. At first, skepticism returned, as it always does when nature surprises us. Some suggested that her instruments must be miscalibrated. Others wondered if gravity might change its rules over vast distances. But Rubin met each question with quiet patience. She repeated her measurements, refined her methods, and expanded her sample. When the results came back unchanged, the evidence could no longer be ignored. The galaxies weren't misbehaving. They were revealing the invisible scaffolding that holds them together. What made Rubin remarkable was not just her precision, but her grace. She never claimed to have overturned the universe. She spoke instead of discovery as a form of listening. "We are still groping for understanding," she once said, not in defeat, but in wonder. If every galaxy required a halo of unseen matter to remain intact, then dark matter was not rare or exotic. It was everywhere, woven through the cosmos, shaping its structure from the smallest clusters to the grandest filaments. The bright stars and glowing clouds we see are only the surface of a vast hidden ocean. Rubin did not pretend to know what dark matter was made of: tiny particles, strange fields, or something beyond imagination. She simply knew it had to be there. Her calm conviction changed astronomy forever. The universe became heavier, stranger, and more beautiful than anyone had dared to believe. For every visible point of light, there is an ocean of unseen mass, keeping it steady. And perhaps that is the quietest wonder of all, that so much of existence lies beyond our sight, yet its influence shapes everything we love. Even in darkness, there is structure. Even in emptiness, there is balance. The galaxies do not need brighter stars to stay together. They are held by the patient weight of the invisible, by the gravity of something that shines not at all, yet keeps every spark in its rightful place. When Vera Rubin passed away in 2016, the scientific world paused, not only to mourn a brilliant mind, but to honor the gentleness of her curiosity. She had shown that science, at its heart, is not conquest but companionship with the unknown. A flat line on a graph can speak more truth than a burst of flame in the sky, if we have the patience to listen. The galaxies she studied still turned tonight calm, elegant, and quietly rebellious, reminding us that light is not the only language of the cosmos. Behind every star is the quiet pull of the unseen. Behind every discovery is someone who noticed when the universe refused to behave as expected. The light gives us beauty, the dark gives us truth. Between them lies the heartbeat of creation itself, a pulse so steady that even time seems to rest upon it. Close your eyes and imagine those distant spirals turning endlessly through space, their luminous arms held in place by the tender gravity of something unseen. That invisible hand, patient, faithful, and silent, is what keeps the cosmos whole, guiding its slow dance through eternity. Gravity has always been the universe's quiet truth teller. You can hide from light, but never from its pull. It reveals what brightness cannot: the weight of things, the ties that bind them, the unseen shapes that light only hints at. Wherever matter exists, gravity speaks in a whisper that cannot be silenced. It bends the paths of stars, gathers galaxies into its arms, and curves the very fabric of space itself. In a cosmos where so much hides beyond sight, gravity is the one voice that never lies. Einstein taught us that gravity is not a string pulling from afar, but the shape of space and time woven together. Imagine the universe as a vast sheet, soft yet unbreakable. Every object with mass, stars, planets, clouds of gas, even you presses gently into it, dimpling the surface. The heavier something is, the deeper its indentation becomes. Light, moving across that fabric, does not travel in straight lines. It bends and curves along those invisible slopes, following the shape of the terrain. So even though dark matter gives off no glow, gravity betrays it. Light from distant galaxies bends as it passes through those hidden valleys. Sometimes it stretches into arcs. Sometimes it splits into twins or triplets of the same galaxy, duplicated across the sky. Astronomers read these distortions like ripples on a pond, tracing where the invisible mass must lie beneath. Gravity leaves fingerprints everywhere, and the patient eye can follow them. It's a little like standing at the edge of a quiet lake. You cannot see the fish below, but the surface tells you when something large moves beneath. The ripples reveal what hides in the deep. Every curve of starlight, every strange twist of brightness is a ripple in the cosmic water. Gravity, ever honest, gives the secret away. To make sense of it, picture the universe as a slow, winding river. The galaxies are its surface reflections, beautiful, fleeting, full of shimmer. Beneath them flows a deeper current, unseen but immensely powerful. That current is dark matter, gliding through everything, shaping what moves above. You cannot dip your hand in and feel it, yet everything you see drifts according to its flow. For all its strength, dark matter is astonishingly well behaved. It never crashes or flares. It doesn't collide with itself or scatter light. It passes through the ordinary world as though the two belong to different realms. Physicists call it non-collisional. Ordinary matter, everything that builds us, our world and the stars, interacts through light and electricity. It bumps, clumps, and glows. Dark matter does none of that. It is gravity alone that binds it to the rest of existence. Because it ignores light, dark matter became the first architect of structure in the early universe. When everything burned hot and bright, ordinary matter could not settle. Photons, particles of light, kept slamming into charged particles, stirring them like a storm. The young cosmos was a seething ocean of radiation and motion. But dark matter floated apart from that chaos, untouched by light's push. Quietly, patiently, it began to gather itself, forming invisible knots and filaments. Those would become the gravitational wells into which ordinary matter would eventually fall. When the universe finally cooled, light released its grip, atoms formed, and the bright gas began to sink into the hollows dark matter had prepared. Stars lit within those wells. Galaxies spun into being. The first cosmic structures rose like frost on a window pane, delicate, ordered, guided by a force that asked for no recognition. Dark matter never built galaxies by hand. It shaped the stage on which they could appear. The irony is that gravity itself is the weakest of all the fundamental forces. It's so gentle that you can lift your hand against the entire pull of the Earth. Yet, over cosmic distances, that gentleness accumulates. It is persistence, not strength, that lets gravity sculpt the universe. Over billions of years, it has rearranged stars, merged clusters, and coaxed galaxies into spirals and chains. Every gleaming arc of light carries the soft imprint of that invisible hand. Sometimes, the universe shows the proof in ways that cannot be ignored. When two clusters of galaxies collide, their luminous clouds of gas slam together and slow down, heating into X-ray bright knots. But their dark matter halos pass right through one another, untouched and silent. The light pauses, the gravity does not. This ghostly separation is one of the clearest signs that dark matter is real, a moment where the unseen moves freely while the visible hesitates. The cosmos performs its own experiment, and we are allowed to watch. Through these cosmic collisions, astronomers glimpse the invisible currents beneath the smooth surface of the universe. The galaxies drift and merge, the light stretches and warps, yet the pattern never loses coherence. Gravity leaves behind a signature that repeats across time. It's written in the arcs of light, in the curves of motion, in the structure of everything that endures. All we have to do is learn to read it. Everything we know about dark matter comes not from seeing it directly, but from the quiet consequences of its pull. Imagine trying to understand the shape of an unseen animal only by how it stirs the grass. The universe offers us the same kind of puzzle. Over decades, astronomers have traced its outline from motion and distortion, piecing together a portrait made of absence. We now know that dark matter forms halos around galaxies, linking them with unseen bridges and keeping the cosmic structure intact. It does not break the laws of physics. It completes them. Without dark matter, the equations predict chaos. Stars would drift apart, clusters would dissolve. The delicate order of galaxies would never take form. With it, everything finds balance. Gravity sketches its curves on an invisible canvas, and dark matter supplies the texture that makes the picture whole. If light is the painter that colors the universe, gravity is the pen that draws its lines. Every orbit, every spiral, every glimmer we admire has been drawn upon a framework that light cannot reveal. Follow those lines far enough, and they connect into a grand design, a web that stretches across billions of light years, delicate yet vast. The invisible doesn't hide from us out of malice. It simply doesn't need to shine to exist. When astronomers began mapping the universe in 3 dimensions, they expected to see galaxies sprinkled more or less evenly, scattered like dust across infinite blackness. But what emerged was something else entirely, a magnificent network of filaments and nodes, woven from invisible threads. The galaxies glowed along those threads, like dew catching light on the strands of a web. Between them lay enormous voids, cosmic abysses so empty that a single galaxy could drift for hundreds of millions of light years without finding another. This immense pattern became known as the cosmic web. It is the skeleton of the universe, the dark scaffolding upon which all light is hung. The first time astronomers saw it mapped out in data, it was like catching a glimpse of the universe's own blueprint. The delicate filaments stretched across the heavens, crossing and merging into dense clusters at their intersections, surrounded by peaceful oceans of nothing. It's hard to imagine such structure arising from the near-perfect smoothness of the early universe. Back then, matter and radiation were almost evenly spread, with only tiny ripples, differences of 1 part in 100,000. Yet those faint ripples became seeds. Where there was slightly more matter, gravity drew more in, deepening the hollows, forming the first knots. Billions of years later, those knots grew into filaments, clusters, and galaxies. Dark matter was the silent builder of it all. Ordinary matter was restless in those first ages, pushed around by light, too hot to hold still. But dark matter was immune to light's pressure. It gathered early, forming invisible rivers that shaped the flow of everything that came after. When the ordinary matter finally cooled, it drifted into those channels, collecting in the grooves like sand settling in a riverbed. Within those deep valleys, the first stars were born. The result is an astonishing harmony. bright galaxies tracing the contours of an unseen map. Each filament stretches across unimaginable distances, hundreds of millions of light years long, slender as threads, strong as destiny. If you could step outside the universe and look down upon it, it might resemble a living brain, a tangle of glowing veins pulsing softly in the dark. Astronomers describe this structure in the language of life: filaments, nodes, clusters, and voids. The filaments are the great bridges of the cosmos, carrying matter like highways of gravity. The nodes are where those bridges meet, the heavy hearts of clusters rich with galaxies. And the voids, those vast, echoing spaces between, are the silences that let the music breathe. The universe is mostly empty, yet that emptiness gives meaning to the light. To map such a thing, scientists have spent decades surveying the sky, recording the positions and distances of millions of galaxies. When they plot them in 3 dimensions, a breathtaking picture emerges, not a random scatter, but an elegant lacework of structure. Each line hums with gravity's quiet insistence. Each hollow holds the memory of balance. Even more beautiful is how faithfully computers can recreate it. Cosmologists feed the simplest ingredients into their simulations: expanding space, gravity, and a form of dark matter that moves slowly and interacts little. From that humble recipe, a digital universe unfolds. Over billions of simulated years, tiny clumps merge into great filaments and dense nodes, matching what our telescopes see in the real sky. It is one of the great triumphs of science that from simple beginnings in the patient hand of gravity, the universe naturally weaves itself into a web. The model they use carries a name that sounds almost lyrical: lambda cold dark matter. The lambda stands for dark energy, the mysterious pressure causing the universe to expand faster and faster. Cold means that dark matter moves slowly, allowing it to clump instead of slipping through space too swiftly to form structure. Together, dark matter and dark energy compose about 95% of all that exists. The rest, the stars, planets, dust, and gas that fill our skies, makes up barely 5%. It's humbling to realize that everything we see, everything that glows, is just the faint shimmer outlining a much grander design. The cosmic web is a masterpiece. Painted in reverse, its true lines drawn not by light, but by darkness. The filaments are narrow and bright, the voids wide and deep. The universe is mostly empty, but that emptiness is not lonely. It is the space that allows structure to breathe. Even the way galaxies spin and grow seems to obey this hidden geometry. They tend to align along the filaments that feed them, their rotations following the slow flow of matter through the web. It is as if the whole universe shares one ancient choreography, every galaxy moving to gravity's long, slow music. To picture it, think of frost spreading over glass, or veins branching through a leaf. Simple rules, repeated endlessly, give rise to infinite variation. Gravity does the same, sculpting order from chaos, with nothing more than time and patience. And then there are the voids, the immense, tranquil spaces between the threads. Some stretch hundreds of millions of light years, containing fewer galaxies than you could count on your fingers. They are not desolate, only serene. They are the pauses that make the song legible. Without them, the web would be nothing but noise. From a distance, the cosmic web looks eternal, but it too evolves. Galaxies slide along its filaments, merging, growing, changing. The voids expand, pushing the bright threads farther apart, as the universe itself stretches. One day, far in the future, many of those glowing bridges will fade beyond sight, yet the pattern will remain, the quiet architecture of gravity and time. For now, it shines like a net of lanterns across the deep. Galaxies glow like cities in the night, connected by roads of unseen matter. The web is order born of silence, the universe discovering balance in the dark. When astronomers look upon it, they aren't simply charting stars. They are reading the autobiography of creation itself. Every filament, every void, every curve is a sentence in gravity's long story, a story still being written in the quiet ink of the unseen. The cosmos does not hide its meaning. It hums it softly. The shape of the universe is not random. Its beauty is deliberate, written in the patient handwriting of time. Light shows us color, but gravity sketches form. Together, they tell the oldest story. There is how darkness shaped the stage so that light could begin its dance, how the unseen gave birth to everything that glows. And yet, even light, that messenger of the visible, is never truly free. To our everyday senses, it feels obedient and straight, a beam through a window, a clean slice of brightness across the floor, a torch cutting neatly through the dark. We are taught to trust in straight lines, but the universe writes in curves. Out there, light bends, twists, even loops back upon itself, not by choice, but because the very fabric it travels through is curved. The reason is gravity's quiet art. Space and time are not empty backdrops. They are the pliant stage upon which everything plays. Every star, every planet, every cloud of gas presses gently into that fabric, shaping it. Heavier things press deeper, and in doing so, they change the paths that light can take. A beam of light follows the curves of that terrain, like a river tracing the valleys of the land. It does not turn of its own will. The road beneath it simply bends. This bending of light has a name: gravitational lensing, and it is one of the universe's most elegant tricks. Imagine placing a clear glass bowl over a field of stars. The light behind it warps, stretches, and swirls into arcs. Some stars seem to double or vanish. Others brighten, magnified by the curve of the bowl. In space, clusters of galaxies act like that invisible glass. Their immense gravity bends the light of faraway galaxies behind them, distorting it into shimmering rings and graceful curves. To an astronomer, these distortions are not accidents, but language. They are the handwriting of gravity, tracing out where invisible mass lies hidden. When the bending is strong, a background galaxy can be stretched into a long arc or copied around the cluster in a complete circle, a luminous ring of light known as an Einstein ring, named for the mind that first imagined such a thing. The name sounds grand, but the phenomenon feels almost tender, light being guided, not forced, by the weight of space itself. Even the faintest bending, what astronomers call weak lensing, matters. Across vast sweeps of sky, light from distant galaxies is subtly stretched or sheared. Alone, the change is imperceptible, but add the pattern of thousands together, and a map begins to form. The distortions reveal where the unseen mass must be, tracing the quiet bones of the cosmos. It's like watching the sway of grass in a breeze to learn the shape of the wind. There's something beautifully poetic about it. Light cannot touch dark matter, cannot bounce from it or illuminate it, and yet, by obeying gravity's shape, it reveals dark matter's presence perfectly. The universe uses light as ink, sketching the contours of what refuses to shine. The more we learn to read these delicate lines, the more detailed the hidden picture becomes. One of the clearest examples of this interplay between light and dark came from a cosmic collision known as the Bullet Cluster, two massive clusters of galaxies that crashed together roughly 150 million years ago. When astronomers looked at the aftermath, they found that the hot gas, the glowing part we can see, had slowed and piled up in the middle, radiating in X-rays like embers in the night. But the invisible mass, revealed by gravitational lensing, had passed straight through, unhindered. It was as if two transparent ghosts had drifted through each other, while the visible debris lagged behind. The separation was stark. The light in one place, the gravity in another. If the universe's gravity came only from what we can see, the two should have aligned, but they did not. The lensing showed that most of the mass had moved on without slowing, untouched by collision. The Bullet Cluster became one of the most persuasive pieces of evidence for dark matter, an accidental experiment written across millions of light years. Dark matter, it seemed, behaved like a ghostly sea, flowing freely while the ordinary world collided and burned. It neither heated nor scattered. It simply moved through, calm and unbothered. And because gravitational lensing traces mass itself, not light, it revealed that the universe's weight resides where brightness does not. Gravitational lensing has since become one of astronomy's most trusted tools, a way to weigh the cosmos without touching it. Every lensing arc is a scale, every curve a measurement of how much gravity, and thus how much mass, lies behind it. By mapping these distortions across billions of light years, astronomers can see how structure has grown through time. The light from distant galaxies carries with it snapshots of the universe's past, each warped beam a record of where the dark was strongest and how it shaped the bright. These measurements are so precise that they can now distinguish between theories of dark matter. Cold dark matter, the slow and steady kind, produces the large-scale web we've already traced, the delicate filaments and clustered nodes stretching across the sky. Warm or fast-moving dark matter would smear that pattern, softening its edges. And so, by reading the faint handwriting of bent light, scientists narrow the possibilities of what the invisible might be. Despite the mathematics behind it, lensing is also astonishingly visual. Telescopes capture images of distant galaxy clusters surrounded by arcs of blue or red background galaxies, stretched and magnified by the intervening gravity. Sometimes a single galaxy appears several times, its copies arranged in a circle, like jewels in a cosmic crown. It feels almost mischievous, as if nature itself has been playing with mirrors since long before we learned to make them. There is a quiet irony here too. We use light to see the dark, the very thing dark matter refuses to produce or reflect becomes our most faithful messenger. Light's flexibility, its willingness to bend, becomes a form of honesty. Wherever it deviates, something massive must be tugging on it. The night sky we see is not a perfect window, but a mosaic of distortions, a portrait painted on curved glass. Yet, without that distortion, we would never glimpse the structure behind the shine. Every arc, every smudge, every elongated glimmer in those deep space images is a confession of the invisible. If you could trace those distortions backward, following the light as it winds across billions of years, you would find that the same soft warping appears even in the oldest glow of all the first light the universe ever released. Long before there were stars, before galaxies or even atoms, space was filled with a blinding fog of energy and particles. It was a time when light could not yet roam free, when photons were trapped, forever colliding with electrons in a restless dance. That fog was the young universe, a hot, dense plasma of pure motion. If you could have stood within it, there would have been no darkness, only a featureless brightness so intense it erased every contour. But expansion is a patient artist. As the universe stretched, it cooled. Around 380,000 years after the beginning, electrons and protons finally joined to form neutral hydrogen. The fog lifted. For the first time, light escaped. It streamed outward in every direction, carrying the first clear imprint of existence. That ancient light still travels. After nearly 14 billion years, it reaches us as a faint, cool whisper, known as the cosmic microwave background, the oldest light in the universe. You can find traces of it everywhere, even in the static between channels on an old television screen. It surrounds the Earth. It flows through you, through everything, a soft echo of when the cosmos first became transparent. At first glance, this background glow appears perfectly uniform, a calm wash of light across the entire sky. But when astronomers began to study it closely, they discovered tiny variations, differences in temperature, so small they measured only thousandths of a degree. Those freckles of warmth and coolness were not random. They were the fingerprints of the early universe, the first hints of structure. In those faint ripples lay the story of everything that would come: the galaxies, the clusters, the filaments of the cosmic web. The slightly denser regions were places where gravity had begun to gather matter. The slightly thinner ones became the vast, empty voids. It is, in a way, the universe's baby picture, a map of its first stirring motions. But here lies a remarkable truth. Without dark matter, those ripples would never have grown into anything. The visible matter, the atoms and light we know, was too restless then, pushed and pulled by radiation. Every attempt it made to collapse under its own gravity was undone by light's pressure. Dark matter, untouched by light, was already at work. It sank into clumps quietly, creating invisible wells for ordinary matter to fall into once the cosmos cooled. Dark matter gave the universe a head start. It was the scaffolding upon which galaxies would later bloom. The cosmic microwave background carries its fingerprints, slight imbalances, gentle curves that reveal how the dark was already shaping the bright. Over the decades, satellites like COBE, WMAP, and Planck have mapped that ancient glow in exquisite detail. On their charts, the microwave background appears as a mottled sphere of faint reds and blues, warm where the radiation is slightly stronger, cool where it is weaker. Those colors, subtle as breath, reveal the exact recipe of the cosmos: about 5% ordinary matter, 27% dark matter, and 68% dark energy, the strange pressure driving space to expand ever faster. These numbers aren't guesses. They are written directly into the pattern of that ancient light, measured from the rhythm of its fluctuations, like notes in a cosmic chord. The universe left us an account book carved into radiation, a ledger of creation itself. Each tiny ripple marks where gravity began to pull, where the first seeds of structure were sown. To imagine it, think of a still pond at dawn. The first light of morning touches its surface, and small rings spread outward, silent, perfect. Each ripple remembers an instant of disturbance, a falling leaf, a fish breaking through. Now scale that image up to the size of the universe. Those ripples are the echoes of the Big Bang, and they still move through everything that exists. Even now, those ancient photons wash over Earth by the trillions every second, drifting through our bodies, our atmosphere, our memories. They have traveled for almost 14 billion years, carrying with them the memory of the universe before there were stars, before there was form. It is humbling to think that every picture of a galaxy, every simulation of dark matter, every observation of the cosmic web, all of it traces back to that quiet glow. If the universe had been perfectly smooth, without those tiny imperfections, there would be no stars, no galaxies, no life. Gravity would have had no starting point. The night sky would be an endless, luminous fog. It is the irregularities, the 1 in 100,000 differences that gave the cosmos texture. Perfection would have been sterile. The universe's beauty was born from its flaws. Each new measurement of the cosmic microwave background refines our understanding, and every new look reveals the same truth. Dark matter was the silent partner in all creation, the unseen hand shaping the bright. The galaxies we see now are just the glowing outlines of patterns it first drew. That faint background light is the universe's autobiography, written in the gentlest ink. It tells of a hot beginning, of slow cooling, of invisible forces guiding the visible world long before light could roam free. Those ancient ripples still echo in the galaxies, in the stars, and even in you. When you look up at the night, you're seeing the afterglow of that first whisper, a shimmer that became every constellation, every world, every heartbeat. The echo of the beginning still hums softly all around, carrying the memory of how darkness gave birth to light. But as the first brilliance faded and the universe settled into its long exhale, the light stepped back and the dark took its turn to create. By the time the cosmos was only a few 100 million years old, the glow of its youth had thinned and vanished into the deep. Darkness ruled again, but this was no longer an empty night. Beneath the quiet, gravity was at work. Invisible structures, vast and weightless, were already knitting themselves together, tracing the framework of what would one day become galaxies. It was a darkness full of potential, heavy with unseen design, waiting patiently for the next act of light. Freed from the chaos of light, dark matter had begun to gather under its own soft gravity, pooling and folding into enormous halos, immense spherical cocoons of mass that gave no light of their own. Each halo was a seed, a gravitational womb in which the luminous world would one day take shape. If you could have seen the universe then, you would have found a sea of ghosts, dark, transparent spheres overlapping and drifting, silent but swelling with promise. Into these hollows, ordinary matter began to fall. Thin clouds of hydrogen and helium cooled as they sank into the gravity wells dark matter had carved. As the gas gathered, it began to swirl, to compress, to break apart into clumps. And somewhere within those clumps, the pressure grew fierce enough for fusion to begin. The first stars flickered to life like tiny sparks in endless shadow, igniting where invisible hands had pressed the gas tight. It's easy to imagine that moment as the universe's first breath, a sudden, trembling shimmer of light rising through a field of darkness. Dark matter was the potter, and the visible universe was its clay. It shaped without revealing itself, steadying the fragile balance of matter, guiding the formation of galaxies with patient strength. Without its structure, this process would have been painfully slow, perhaps never complete. The night sky might have remained almost blank, dotted only with a few lonely embers instead of hundreds of billions of stars. The halos did not all appear at once. Small ones formed first, merging and merging again to make larger and larger structures. Each collision brought quiet transformation. The dark matter clouds passed through one another like mist, blending to form new, deeper wells of gravity. The gas trapped between them collided, heated, and cooled again, each cycle sparking new bursts of star birth. Over billions of years, this patient dance built everything from tiny dwarf galaxies to vast spirals and elliptical giants. Every galaxy that shines today, including our own Milky Way, sits nestled within one of these halos. The bright disk we see, the elegant spirals, the clouds of dust, the jeweled arms is only a thin layer resting on a vast invisible foundation. The dark halo extends far beyond what any telescope can catch, stretching hundreds of thousands of light years into the quiet. Most of the galaxy's weight lies there, where light cannot go. When astronomers run their great simulations of the cosmos, they often begin with only two ingredients: dark matter and gravity. From that simplicity, a universe grows. Halos bloom like droplets in a mist, gathering, colliding, merging. Add gas to the simulation, and luminous galaxies emerge naturally within those dark cocoons, following the same hidden scaffolding. The light does not lead, it follows. The universe builds from the shadows outward, the unseen forming the mold and the visible filling it in. There's a strange comfort in that thought. For all our fascination with light, the glowing stars, the nebulae, the radiant galaxies, it is the darkness that gives them structure. The halos are like invisible hands shaping clay in the dark, guiding where galaxies will rise and how they will evolve. Even the delicate arms of our Milky Way owe their calm symmetry to the quiet grip of its dark matter halo. Without it, the stars would drift apart over time, slipping away like leaves scattered by wind. In regions where halos formed quickly, galaxies became bright and crowded. Gas rushed inward, ignited in furious bursts of star birth, and spent itself in a blaze of creation. In gentler regions, halos grew slowly, and galaxies unfolded more calmly, their stars forming over long, languid ages. Across the vastness, the cosmic web served as the network that connected them, all great filaments, channeling gas and matter into the waiting halos, rivers feeding the basins where galaxies took shape. The universe became a living map of balance, gravity gathering, light responding, motion finding rhythm. The halos were its basins, collecting the flow of creation. Within them, hydrogen became stars, stars became clusters, and clusters became the glowing hearts of galaxies. Even now, billions of years later, this quiet relationship between the visible and the invisible continues to define the sky. The halos dictate how fast galaxies spin, how heavy they can grow, and how gracefully they move through one another. When galaxies collide, it is their halos that meet first immense, soft, overlapping clouds, merging before any star touches another. The brilliant fireworks of galactic collisions that telescopes capture are only the luminous echo of that deeper, darker union beneath. Astronomers can even trace dark matter's influence on smaller scales. Tiny satellite galaxies orbiting giants like our Milky Way dwarfs, made of only a few thousand stars, are held together by dense knots of dark matter. Without that hidden weight, their fragile structures would be torn apart by tidal forces long ago. In this way, dark matter acts as a cosmic glue, preserving what would otherwise dissolve, keeping delicate forms intact through eons. If dark matter did not exist, the universe would look nothing like it does now. The early gas would have remained smooth and diffuse, never gathering quickly enough to spark the first stars. Galaxies, if they formed at all, would have been small, rare, and dim. The night sky would be nearly blank, with only a few faint smudges of light instead of the glittering ocean we know. The dark, it turns out, made the light possible. There is a quiet poetry to that balance. The first stars born inside the halos lived brief, radiant lives. They burned fiercely, flooding their surroundings with ultraviolet light that slowly cleared away the lingering fog of hydrogen. When they died, they scattered carbon, oxygen, and iron elements that would one day form planets, oceans, and living creatures. In that sense, dark matter didn't just shape galaxies, it prepared the stage for life itself. Astronomers continue to study these halos, measuring how galaxies move within them, how gas flows through them, how they evolve across billions of years. The details are intricate, but the melody is simple. Where dark matter gathers, light follows. The halos form the invisible wells, and the stars are the ripples that shimmer upon them. If you look at an image of a galaxy, the graceful whirl of Andromeda, perhaps you see a structure glowing in silence, a swirl of light framed by dark. But what holds that beauty in place lies far beyond what you can see. The spiral arms trace the gravity of something much larger, quieter, and unseen. Every rotation, every shimmer of light is a testament to the hidden shape that contains it. Strip away the stars, and the galaxy would not vanish. Its true form would remain, a dark, vast halo of invisible matter, hundreds of thousands of light years wide, sculpted by time and gravity alone. It is still growing, ever so slowly, as stray matter falls into its embrace. Dark matter builds with patience. It does not shine, but it holds. Every galaxy in the universe, no matter how brilliant or chaotic, lives inside one of these halos, a vast cocoon of darkness wrapped around a luminous core. If you could see it, it would look like a glass sphere surrounding a lantern, clear, weighty, and quietly immense. The glowing heart in the center, the stars and gas, are only a hint of the whole. The halo is not a shell, it is a foundation. It outweighs the visible galaxy many times over. Its gravity, the silent architect that keeps every star in place. The bright spiral we see is just the crest of a much deeper wave. The stars are the light on the surface of an unseen sea. Within the halo, the dark matter particles move in swarms, orbiting one another under the same shared gravity, never colliding, never slowing, passing through each other like ghosts. They form a stable cloud, calm, balanced, ancient. The luminous galaxy is only the surface bloom of that invisible ocean. The very idea of halos came naturally once astronomers saw how galaxies truly spin. The stars in the outer regions move too quickly to be held by light alone. The simplest, most beautiful explanation was that each galaxy sits within an extended reservoir of unseen mass. Include the halo, and suddenly everything fits. The rotation steadies, the galaxy holds together, and the universe's strange logic becomes harmonious. The halos also bind families of galaxies together. Around our own Milky Way drift dozens of small companions, dwarf galaxies so faint they are barely more than whispers of light. Yet they remain bound, circling slowly through the dark. The halo's gravity reaches out, keeping them close, like distant lanterns caught in the same invisible current. Inside this gravitational bowl, stars and gas may move freely, but they cannot leave. The walls are deep, curved, and patient. Even at hundreds of kilometers per second, the stars remain captive, their paths bent gracefully back toward home. When galaxies merge, their halos merge first. They overlap and mingle, absorbing one another long before the luminous centers collide. What looks like a violent event through a telescope is, in truth, a slow and graceful exchange. Two invisible clouds folding together until they become one. Out of that long embrace, a new galaxy is born, more massive, more luminous, and once again cradled by a single, larger halo. Yet even among these silent guardians, no two are quite the same. Some halos hold their gravity tightly, their invisible hearts compact and fierce. Others are gentler, more diffuse, like fog drifting through the dark. Astronomers have spent decades trying to understand how dark matter arranges itself inside these unseen cocoons. In the elegant language of simulations, halos often form sharp, dense cores, what scientists call cusps. But when telescopes turn toward real galaxies, especially the smaller, more fragile ones, the story softens. Their centers seem smoother, flatter, less intense. This quiet mismatch between theory and sky, the core cusp problem, suggests that the universe still keeps a few of its craft secrets to itself. Perhaps dark matter behaves in ways we haven't fully imagined, interacting slightly with itself, softening its own gravity in the middle. Or perhaps ordinary matter, through its messy energy supernovae, collapsing gas clouds, and tidal pulse, has gradually reshaped the halos from within, stirring them like gentle tides over billions of years. Whatever the cause, the halos endure. They have survived collisions and mergers, cosmic expansion, and galactic tempests. They are the most patient structures in existence. While stars flare and fade, halos keep their quiet watch, holding the shape of the universe steady, even as light comes and goes. To picture their scale, imagine our Milky Way suspended in its invisible shell. The bright disk of stars that streaks across the night sky stretches about 100,000 light years from end to end. But the dark halo surrounding it extends at least 10 times farther out, to 1,000,000 light years or more. It reaches so far that our neighboring giant, the Andromeda Galaxy, is already brushing against it. The halos of both galaxies are mingling now, long before the visible spirals will merge. In roughly 4 billion years, when their luminous arms finally entwine, their halos will have already been dancing together for most of cosmic history. Our halo is not empty. It holds subtle structures of its own delicate filaments of stars called stellar streams. These are the remnants of smaller galaxies and clusters that strayed too close and were slowly torn apart by gravity. Their stars spill outward along curved orbits, leaving behind luminous trails that weave across the sky. Each one is a scar of an ancient encounter, a visible reminder that the Milky Way is still growing, still absorbing, still rewriting itself. Astronomers trace these streams with exquisite care. By studying their shapes and motions, they can infer how the dark matter halo is arranged, its density, its symmetry, its hidden currents. The stars act like glowing tracers, drifting in a transparent wind. From their paths, the underlying gravity becomes visible. It's a kind of celestial archaeology. Light, used to map shadow. The halo's role reaches far beyond mere stability. It regulates the galaxy's evolution, serving as both cradle and gatekeeper. gas falling into the halo is heated by compression, forming a warm, diffuse envelope around the galaxy. Some of that gas cools and rains down again, feeding new generations of stars. Other streams escape, driven out by the fierce winds of supernovae and black hole jets. The delicate balance between what falls in and what flows out decides the pace of a galaxy's life. In that sense, the halo acts like a cosmic thermostat, steadying the rhythm, deciding when the light brightens and when it rests. For something invisible, halos wield extraordinary influence. They determine how fast a galaxy spins, how bright it becomes, and how long it can endure. Without them, galaxies would be fragile, ephemeral bursts of light that fall apart within a few rotations. With them, the stars can circle for billions of years, secure in the dark's embrace. It's a soothing thought. Each galaxy, a lantern suspended in a glass sphere, its glow sustained by invisible arms that cradle it from every direction. The light and the dark are not rivals, but partners. The stars may catch our eyes, but the halo gives them a home. And the pattern holds everywhere. Every spiral, every elliptical, every faint smudge at the edge of observation sits inside its own unseen shell. Even in the loneliest stretches of space, where galaxies are few and far between, each one is enveloped in its private sphere of gravity. When you look up on a clear night and see the Milky Way as a misty band across the sky, you're gazing at only its luminous heart. Beyond those visible stars lies a vast, silent halo, ancient and enduring, holding everything in place. We drift within that invisible sea, as much a part of it as the stars themselves. The halo does not shimmer or sing, yet its quiet pull defines the shape of the heavens. It is gravity's masterpiece, both infinite and intimate, steady and unseen. The Milky Way's glow is the visible surface of a deeper structure, a lantern burning within a vast sphere of glassy dark. To most of us, our galaxy feels familiar, a great spiral of stars curling gracefully through space. But that glittering disk is a thin shell on the surface of something far larger. The Milky Way is not just a wheel of starlight. It is an island of brightness, afloat in an invisible ocean. We live deep inside this halo, surrounded on all sides by dark matter that neither touches nor resists us. Every planet, every comet, every beam of starlight moves through it like a swimmer through still water. There is no drag, no friction, no sound, only gravity's steady influence, defining the gentle curves of motion. Even the sun is not fixed in place. It races around the galactic center at about 220 kilometers per second, completing one grand orbit every 230 million years. As it moves, it carries the solar system through the Milky Way's dark halo, a steady voyage through a current we cannot see. You might imagine the solar system as a small vessel gliding through calm, invisible tides. The dark matter neither pushes nor pulls directly, but it defines the contours of the sea in which we sail. If our eyes could see dark matter, the Milky Way would appear as a glowing sphere of faint gray light, stretching far beyond the spiral arms. The visible galaxy would seem like a candle at the center of a vast glass globe. That globe extends hundreds of thousands of light years beyond the outermost stars, wrapping around us completely. Within it, everything that shines is but a surface ripple on a deep gravitational ocean. For astronomers, studying this hidden ocean requires indirect art. They cannot see the dark matter itself, but they can chart how stars move within its pull. The motion of each star becomes a clue. When plotted carefully, The pattern reveals the halo's invisible shape, just as the drift of seaweed reveals the current below the surface. Among the most graceful of these tracers are the stellar streams, those thin, ghostly ribbons of stars winding around the galaxy. Each one is the remnant of something once whole, pulled apart by gravity but still tracing the memory of its orbit. These luminous filaments loop across the sky, wrapping the Milky Way in delicate lace. From their curves, astronomers can reconstruct the gravitational landscape of our halo with remarkable precision. It's as though the galaxy's skeleton has been revealed through glowing fractures, scars illuminated by starlight. The most famous of these streams is the Sagittarius stream, the lingering remains of a small galaxy now being absorbed by our own. Its arc of stars wraps around us like a pale ribbon, a whisper from an encounter that began hundreds of millions of years ago. Such streams remind us that the Milky Way's halo is not smooth. It carries ripples, knots, and gentle distortions, records of every collision and merger that has ever passed through. Each new satellite galaxy leaves its fingerprint in the dark, a subtle echo that can last for billions of years. Though we drift inside this vast, unseen realm, dark matter never truly touches us. Its particles pass effortlessly through the Earth, through our bodies, through the walls around us. Countless times, every second, we feel nothing. No wind, no weight, no resistance. At first, the thought is eerie. Then, it becomes strangely serene. The dark matter seed does not disturb, it simply carries. It is the calm in which all motion happens. The halo's gravity anchors the Milky Way, keeping the outermost stars bound as tightly as those near the center. Without it, the edges would unravel into space, dissolving into the intergalactic dark. The halo is the quiet heart of stability, the unseen companion to every brilliant star. Astronomers are still learning its exact shape. Some evidence hints that it might be slightly flattened, as if pressed gently at the poles. Others suspect it is lopsided, tugged and warped by ancient mergers or the nearby gravity of Andromeda. Whatever its true form, it defines the real size of our galaxy, a size far greater than the delicate spiral we can see. The halo also acts as a net, catching and keeping smaller galaxies that wander too close. The faint smudges we call satellite galaxies, tiny companions orbiting the Milky Way, survive because they are caught in this web of gravity. Over time, some will spiral inward and merge with us, feeding our growth, thickening the halo, enriching the dark. Our galaxy is still assembling, still sculpting itself in silence. It is humbling to realize how thoroughly we are held by the unseen. Every orbit, from the sun's long journey around the galactic core to the subtle drift of a comet at the edge of the system, follows the curves of an invisible map. We often speak of space as empty, but it is not emptiness that carries us. We move through a sea of substance that does not shine, a vast gravitational ocean whose currents define everything we see. So when you look up at the Milky Way on a clear night, remember that glowing ribbon of stars is just the thinnest surface of something immense. We are not outside it, looking in. We are inside it, adrift in the dark. The halo surrounds us completely, silent, patient, and kind. It gives our galaxy its shape, its steadiness, its long life. It is why the Milky Way has endured for billions of years, why its stars keep their rhythm, why the sun still sails its path unbroken. We are passengers within a vast, invisible vessel, a ship of light carried by the dark. We sail through space, guided by a force we cannot touch, held in balance by an ocean we can never see. The halo is not merely the heart of our galaxy. It is the quiet reason the galaxy exists at all. By now, the case for dark matter feels almost unshakable. Galaxies spin too quickly. Clusters of galaxies cling together when visible gravity alone should let them drift apart, and the light of distant objects bends more strongly than luminous mass can explain. The universe behaves as though an unseen weight runs through it, invisible yet undeniable. Before scientists could start imagining exotic new particles, they had to ask a humbler question. Could the darkness be ordinary after all? Could we simply be missing something familiar that hides too well for our instruments to find? It was a reasonable place to begin. Perhaps the missing mass wasn't something alien, just matter too faint to register. Maybe the cosmos was filled with a multitude of invisible stars, tiny, cold suns that never quite ignited, or the faint white remnants of those that had already burned out. For a time, that idea had a certain charm. Astronomers imagined galaxies teeming with brown dwarfs, veiled stars hovering forever at the edge of brilliance, or white dwarfs, the dense cinders of ancient suns. Even rogue planets, great worlds without homes, drifting silently between the stars. Collectively, these objects were given a name, both whimsical and serious: MACOs, short for massive, compact, halo objects. The term was chosen partly in jest, but the idea was elegant. Perhaps the halos we could not see were simply crowded with unseen but perfectly normal matter. If so, dark matter would not be dark in principle, only in practice, a veil, not a mystery. But as telescopes grew sharper and surveys more complete, the numbers refused to cooperate. Even when astronomers searched indirectly, looking for brief flashes of starlight as a macho passed in front of a background star, bending its light in a phenomenon called microlensing, the evidence fell short. A few such events were seen, confirming that MACOs exist, but nowhere near enough to explain the enormous, hidden mass that galaxies require. You could fill the heavens with brown dwarfs and still fall short by a factor of 10. The universe's invisible weight demanded something stranger. Perhaps, some thought, the answer lay not in compact bodies but in diffuse ones. Could the halos be made of cold gas, vast, unlit oceans of hydrogen floating through space? Hydrogen, when chilled enough, gives off no light at all. It could hide easily, transparent and silent, but nature is never perfectly quiet. Cold hydrogen interacts with cosmic rays and starlight, producing faint radio emissions. Sensitive telescopes tuned to those frequencies should reveal it. They did not. A trace here and there, yes, but not nearly enough to fill the void. Dust was next on the list of suspects. After all, dust pervades the universe, tiny grains of carbon and silicate that block, scatter, and soften light. What if the cosmos was simply dustier than we thought? But dust has a habit of giving itself away. It absorbs visible light and re-emits it at longer infrared wavelengths. If the universe were filled with enough dust to account for the missing mass, the entire sky would glow faintly in infrared. Observatories searched for that glow and found nothing. The darkness remained stubbornly pure. With stars, gas, and dust eliminated, the mind naturally turned to the universe's most secretive residents, black holes. What if space were sprinkled with countless small black holes, objects that have gravity, no light, and a taste for solitude? It was an enticing hypothesis. Black holes are the universe's great simplifiers, erasing all details except mass. If there were enough of them, they could quietly explain everything. But data, as ever, had the last word. If the Milky Way's halo were full of black holes, their gravity would betray them. Each one would act as a lens, briefly brightening distant stars as it drifted past. Astronomers watched for these flickers for decades. A few appeared too few. Even if every candidate turned out to be real, their combined weight would not come close to the required total. And large black holes, the kind formed from collapsing stars, would reveal themselves another way. Their collisions would send ripples through space-time, a constant background hum of gravitational waves detectable by instruments like LIGO and Virgo. No such steady signal has been heard. The sky remains too quiet. There is, however, one corner of the black hole story that still tempts physicists: primordial black holes, ancient relics that might have formed in the universe's first moments before stars or galaxies. In those violent early conditions, regions of unusually dense matter could have collapsed directly into tiny black holes. If enough had survived, they might contribute a small fraction of the dark matter we seek. It's a fascinating possibility, but only a fraction. The math refuses to stretch far enough to make them the whole answer. Step by step, the familiar was ruled out. Stars, gas, dust, compact remnants, all could exist, but none could explain the invisible majority. The process was both frustrating and exhilarating. Frustrating because each promising idea dissolved under observation. Exhilarating because what remained was undeniably new. The darkness was not a bookkeeping error. It was a discovery. The cosmos, it turned out, contains not one kind of matter, but two. The ordinary kind that shines and interacts, and another that neither emits nor absorbs light, yet dominates by mass. This realization marked a turning point in modern science. The visible universe, the stars, planets, and all the atoms of human existence is merely the surface of a much larger composition. Without dark matter, galaxies would fly apart, stars would wander, and the cosmic web would never have formed. The darkness is not absence, it is structure itself. Once that conclusion solidified, a new question rose to the forefront. If dark matter isn't made of anything we already know, what is it? Somewhere in the zoo of possible particles, something must exist that carries mass but resists every other kind of interaction. Something that shapes galaxies but passes through walls. To qualify, such a particle must meet three demanding conditions. It must be cold, moving slowly enough for gravity to gather it into clumps rather than smearing it thin. It must be stable, long-lived enough to persist for billions of years. And it must be shy, interacting so weakly with ordinary matter that it leaves almost no trace except gravity's pull. That combination makes dark matter both maddening to detect and tantalizingly elegant. Nature already offers a hint of something similar. Neutrinos, these ghostly particles, born in nuclear reactions, pass through entire planets as though through empty air. Trillions of them stream through you every second. Yet neutrinos are too light and too quick to account for the missing mass. They're more like cosmic sparks than stones. Dark matter must be heavier, slower, more gravitationally bound. One of the earliest and most popular candidates was the WIMP, the weakly interacting massive particle. The name itself feels half serious, half wink, but the physics is sound. A WIMP would be heavy by subatomic standards, massive enough to gravitate strongly, yet almost indifferent to all other forces. The idea's beauty lies in its economy. Particles like this would naturally emerge in many extensions of the standard model of particle physics, especially in frameworks like supersymmetry. In those theories, the lightest supersymmetric particle would be stable and weakly interacting, the perfect recipe for dark matter. If WIMPs exist, they should occasionally bump into ordinary matter. Not often, but sometimes, a rare tap of a ghostly particle against an atomic nucleus. Detecting such a faint interaction requires extreme conditions. Experiments have been built deep underground, where the Earth shields out cosmic noise. Tanks of ultra-pure xenon or argon wait in total darkness for a single flicker of recoil energy, a whisper of contact from something unseen. So far, the silence has been near total. Yet that silence itself is instructive. It tells scientists how strong, or rather, how weak, dark matter's interaction must be. While WIMPs came from high-energy physics, another candidate emerged from an entirely different question. In the 1970 seconds, physicists trying to fix a mathematical quirk in quantum theory proposed a new field, one that would smooth out a symmetry problem in the strong nuclear force. The particle associated with that field was christened the axion. It was introduced as a footnote, a mathematical correction, not as a cosmic player. But then someone noticed, if axions exist, they have exactly the right properties to serve as dark matter. Axions would be incredibly light, perhaps 1 trillion times lighter than an electron, but they could exist in such vast numbers that their combined gravity would outweigh all the visible stars. Rather than behaving as individual particles, they'd act as a kind of collective wave, a gentle oscillation filling all of space. You can imagine it like a violin string vibrating across the entire universe, continuous motion that, when examined closely, seems to resolve into countless faint notes. If axions pass through magnetic fields, they might occasionally transform into photons, particles of light. That means, in theory, we could catch them in the act. Experiments use powerful magnets and ultra-sensitive detectors to listen for that conversion, tuning to frequencies where an axion might sing. None have yet been heard, but the listening continues. Then there is the sterile neutrino, an even quieter possibility. Regular neutrinos already slip through matter with ease, interacting only through the weak nuclear force. But a sterile neutrino would interact not at all. No electric charge, no weak force, nothing but gravity. Such particles could have been born alongside ordinary neutrinos in the early universe, influencing the formation of galaxies without ever revealing themselves. Depending on their mass, they would count as warm, dark matter, fast enough to smooth out small-scale structure, slow enough to let galaxies form. X-ray observations and cosmic background data have placed limits on them, but they remain plausible, lurking between theory and discovery. Each of these candidates, WIMPs, axions, sterile neutrinos, offers a different vision of the unseen. WIMPs are like heavy, sparse boulders scattered through space. Axions are a pervasive mist, an invisible fog of gentle motion. Sterile neutrinos are subtle whispers at the edge of known physics. It's even possible that more than one of these species exists, woven together into the dark fabric that holds the universe. Despite their differences, they share the same 3 virtues. They are cold, stable, and shy. Cold so that gravity can gather them. Stable so that they endure from the dawn of time. Shy so that they neither shine nor scatter light. Those qualities, repeated across theory after theory, are what give scientists confidence they are circling something real. The experiments continue in mountain caverns, in orbiting observatories, in accelerators where particles collide at near light speed. Each attempt is a different way of asking the same question: what exactly is the universe made of? The search has already redefined what we mean by matter. It reminds us that most of what exists does not shine, and yet it is the dark that gives the bright its shape. We are, in a sense, children of that hidden substance, creatures whose atoms dance in the shallows of a deeper sea. The stars tell only half the story. The rest is written in a language we have only just begun to learn. Gravity's grammar, spoken softly in the dark. There's something strangely endearing about the idea that the universe could be filled with ghostly marbles, rolling endlessly through space, an invisible rain of particles gliding through walls, through planets, through you, without ever leaving a mark. We are surrounded by them, soaked in them, immersed in their silent passage. The dark matter candidates are like polite house guests of the cosmos, perfectly well behaved, never disturbing the furniture, yet somehow responsible for holding up the whole house. Each new experiment adds another brushstroke to this invisible portrait, refining the outlines of what might be. Whether the answer lies in heavy WIMPs, feathery axions, or something still unimagined, the search itself has already stretched our sense of possibility. The more we learn about what the universe could be made of, the stranger and more astonishing it becomes, a place where the most important ingredients are the ones that refuse to show themselves. But if these invisible particles truly surround us, if they are streaming through the room right now, through your body, through the walls, through the planet itself, then the obvious question becomes, how do we find them? How do you catch something that slips through everything you've ever built? In principle, these particles should be passing through Earth constantly, trillions of them every second, like a tide of darkness flowing through rock and bone alike. They don't slow down, they don't glow, and they rarely collide. But just maybe, once in a great while, one of them could brush an atom in the right way, a faint nudge, a single recoil, a microscopic whisper. That whisper is what scientists are trying to hear. The search for dark matter doesn't take place in gleaming observatories or orbiting telescopes, but in the loneliest and quietest places on Earth. The experiments are buried far below the surface, beneath mountains, inside abandoned mines, under Antarctic ice places where cosmic rays and radiation from the upper world can't reach. Down there, shielded from the noise of creation, vast detectors wait in the dark, listening for something that may never come. The idea behind them is simple enough to describe and impossibly delicate to execute. If a dark matter particle strikes an atomic nucleus inside the detector, that nucleus should recoil ever so slightly, giving off a tiny flash of light or a microscopic vibration. Catch that flash, record that vibration, and you've caught the invisible. But in practice, it's like trying to hear the fall of a single snowflake during a thunderstorm. These detectors are technological cathedrals of patience. Some use giant tanks filled with liquid xenon, chosen because it's so pure, so quiet, and so good at emitting light when struck. When a rare collision happens, it releases a tiny pulse of ultraviolet light, captured by an array of sensors surrounding the tank. The entire experiment becomes a cosmic eardrum, listening for the faintest tap from an unseen visitor. Others take a colder approach, The super cryogenic dark matter search in Canada uses germanium and silicon crystals cooled to nearly absolute zero. When even the smallest amount of energy hits them, they tremble, producing measurable temperature shifts changes smaller than 1/1,000,000th of a degree. These devices are tuned so precisely that they could, metaphorically speaking, ring from the weight of a snowflake. Each experiment is an act of devotion to precision. Every atom is counted, every flicker scrutinized. The background noise, natural radioactivity, the faint trace of cosmic rays, even the subtle warmth of nearby rock must all be measured, cataloged, and subtracted. The detectors run for years, sometimes decades, often without a single event that can confidently be called dark matter. The silence itself becomes the data. One of the largest and most sensitive of these experiments, Lux Zeppelin, sits almost a mile underground in a former gold mine in South Dakota. Inside, several tons of liquid xenon rest at a temperature just above freezing. The chamber is surrounded by layers of shielding, sensors, and electronics so finely calibrated they can register a single photon of light. If a dark matter particle ever taps a xenon atom, the detector will see a flash no human eye could notice, but the universe might. In Italy, beneath the Gran Sasso Mountains, another vast detector listens in the stillness, buried under a mile of rock. In Japan, the Kamioka Observatory waits in an old zinc mine. Even Antarctica, the most remote of laboratories, has its watchers. The Ice Cube Neutrino Observatory, though designed to study neutrinos, shares the same spirit, an enormous array of sensors frozen deep into the ice, listening for whispers that travel through a medium most people think of as silence. These experiments share a kind of monastic patience. The scientists who tend them are not surrounded by glowing screens and applause. They work in quiet tunnels, maintaining instruments that must never sleep, trusting that the universe will eventually speak. Each non-detection, each stretch of silence, still teaches something. It narrows the range of possible particle masses, refines the limits on how strongly dark matter can interact. Every null result is a contour line on the map of the unknown. And so the years pass. A blip of light appears on a monitor, a strange vibration, a fleeting signal, and the world briefly holds its breath. Was that it? Was that the sound of the unseen touching matter at last? Usually, after months of careful analysis, the answer is no. But someday, the answer may be yes. That moment, when it comes, will be profound. It will mark the first time humanity has directly touched the material that built the galaxies. We will have caught a particle that didn't want to be caught, heard the faintest sound in the quietest cathedral. Until then, the detectors keep listening. The lights remain dim. The world above goes on, unaware of the slow, patient watch being kept far below. Still, there's another way to listen. If dark matter refuses to reveal itself underground, perhaps it can be coaxed into confession by the sky. The universe has been running experiments of its own for billions of years, galaxies colliding, halos merging, particles brushing past one another in the dark. Somewhere out there, among those vast interactions, faint traces might remain. This approach is called indirect detection. Instead of trying to catch a dark matter particle directly, astronomers look for the byproducts of what happens when two dark matter particles collide and annihilate each other. When that occurs, they might produce high-energy gamma rays, positrons, or neutrino signals we can detect even if we never see the particles themselves. It's a bit like searching for footprints instead of the creature. The best places to look are where dark matter should be densest. The center of our own galaxy, for example, is a prime suspect. The Milky Way's core is crowded with stars, dust, and according to models, a massive reservoir of dark matter swirling around the central, supermassive black hole. If dark matter particles occasionally annihilate there, the region should glow faintly in gamma rays, the most energetic form of light. Telescopes like NASA's Fermi Gamma Ray Space Telescope have indeed detected something intriguing: a soft, steady glow of gamma rays coming from the galactic center that doesn't fit any known source. For a time, the data looked like the perfect match for theoretical predictions of WIMP annihilation. Excitement rippled through the scientific world. Had we finally glimpsed the glow of the invisible? As always, the truth proved slippery. The signal was real, but the interpretation was messy. The galactic center is a cauldron of complexity: pulsars, black holes, supernova remnants, and swirling clouds of hot gas. Any of these could produce similar emissions. One team would declare the pattern a smoking gun for dark matter. Another would argue it came from a population of undetected millisecond pulsars. It was like seeing flickers in a fog and debating whether they were fireflies or reflections. Beyond the Milky Way, astronomers turned their gaze to dwarf spheroidal galaxies, tiny, dim satellites that orbit larger galaxies like our own. These systems are almost pure dark matter, with very little background noise from stars or gas-ideal laboratories for indirect searches. Dozens of telescopes have stared at them, hoping to catch the telltale hum of gamma rays. A few hints have emerged, faint upticks in the data, but never the decisive proof. The signals appear, fade, and dissolve back into statistical noise, as if the universe enjoys being coy. Other experiments chase different clues. Some focus on positrons, the antimatter twins of electrons, which might be produced when dark matter particles annihilate. Detectors like AMS-02 aboard the International Space Station have measured unexpected surpluses of positrons in cosmic rays. The pattern is intriguing, but interpretation is difficult. Pulsars and supernova remnants can also produce such particles, muddying the waters. Distinguishing a cosmic message from the natural chatter of the universe is like trying to hear a single violin in an orchestra of thunder. Neutrinos offer yet another trail. If dark matter accumulates in dense bodies like the sun, it might occasionally annihilate inside, releasing neutrinos that escape unhindered. Instruments, such as IceCube, are tuned to catch these ghostly messengers: vast volumes of Antarctic ice, wired with sensors that flash when a neutrino passes through. So far, though, the universe has answered with silence. The challenge in all these searches is the same. Space is loud. The cosmos hums with energy. Cosmic rays, pulsars, jets, collisions, all producing light and particles of their own. Dark matter, by contrast, speaks in whispers. Even if it leaves a trace, that trace must be separated from the fireworks of ordinary astrophysics. It's like trying to spot the reflection of a candle in a storm of lightning. Yet that is precisely what makes the search beautiful. Every unexplained glow, every anomaly, sends scientists back to their models, refining, testing, arguing. The back and forth is the heartbeat of discovery. One year brings excitement, another brings doubt. The universe withholds its secrets, but it keeps us asking better questions. New observatories are on the horizon: the Cherenkov Telescope Array, the Euclid mission, next-generation gamma-ray and neutrino detectors, all built to sift through the noise with unprecedented precision. They will map the sky in exquisite detail, hunting for the faint, diffuse shimmer of annihilating dark matter stretched across the galaxies. There's a certain poetry to this phase of the search. Humanity, with all its limited senses, has built instruments that can listen to the silence between stars, tuned to hear the faint echo of creation itself. We've buried ears in the rock and hung eyes in orbit, all for the chance to glimpse the invisible hand that sculpts the cosmos. Whether the signal comes from beneath the Earth or from the heart of the Milky Way, it will tell us the same thing: that we were never walking through emptiness at all. We have always been moving through presence, vast and unseen, patient as time itself. We are, in a sense, hunting for shadows made of light, tiny signatures that appear only when the invisible briefly touches the visible. It's a dance of opposites, where darkness might finally reveal itself, not by its absence, but by the glow it leaves behind. Each experiment joins this slow choreography, searching for a moment when silence stirs. Even when nothing appears, that nothing matters. Every non-detection sharpens the picture. Each quiet result trims the edges of theory, closing some doors and pointing toward others. In this field, absence itself is a kind of compass. It marks the faint horizon we keep pushing forward. The lack of a signal is not the end of the story. It is the boundary line of progress. If we cannot yet hear the whispers of dark matter deep underground, and the sky gives us only uncertain murmurs, then perhaps it's time to look elsewhere, into the realm where the smallest pieces of reality collide. If the universe won't show us its secrets naturally, maybe we can coax them into being. Astronomers look outward, but physicists have another strategy. They try to rebuild the beginning of everything. In laboratories across the world, they smash known particles together at nearly the speed of light, hoping that in the aftermath, something unfamiliar will emerge. The logic is simple and beautiful. The early universe was a furnace of collisions. If dark matter was born in that chaos, then somewhere in the storm of energy, we might recreate the same conditions and perhaps, for a fleeting instant, recreate the dark itself. This is the dream behind particle colliders machines that do not just observe the universe, but imitate its creation. The most ambitious of them all sits buried beneath the French-Swiss border. The Large Hadron Collider, a ring of steel and magnets stretching 27 kilometers through the Earth. Inside, protons race through its circular tunnels at nearly the speed of light, guided by superconducting fields and then directed to crash head-on. When they collide, they reproduce the energy and density that existed only moments after the Big Bang. Out of those brief, violent encounters, new particles are born, some familiar, others fleeting echoes of the universe's infancy. The detectors surrounding the collision points record these storms of debris, cascades of electrons, muons, and protons, spiraling outward like sparks. Most of what appears is well known, but sometimes the numbers don't quite add up. Physicists can measure exactly how much energy goes into a collision and how much comes out. If even a small portion vanishes, if there's energy unaccounted for, that missing piece may belong to a particle that slipped through the detectors without a trace. This phenomenon is called missing energy, and it's one of the most tantalizing clues of all. When energy disappears without explanation, it may have gone into creating something that doesn't talk to light, something like dark matter. It's a simple but profound accounting exercise. The universe keeps perfect books. Energy can't simply vanish. So, if the math doesn't balance, something unseen must be carrying the remainder away. To find these disappearances, detectors such as Atlas and CMS at the LHC record billions of collisions per second. Sophisticated algorithms sift through that avalanche of data, searching for telltale imbalances, patterns where the visible particles rush in one direction, while an invisible partner slips silently the other way. These experiments don't see dark matter directly. They see its shadow, drawn in the shape of missing energy. The search complements what astronomers do on a cosmic scale. While telescopes and underground detectors show where dark matter is, colliders try to reveal what it might be. It's like investigating a mystery from both ends. One team follows footprints, the other tries to make the suspect appear. The idea of creating dark matter may sound impossibly grand, but it's quite natural. In the early universe, all particles danced between forms, colliding, annihilating, reforming. To make dark matter, we only need to replicate those ancient conditions, though the recipe is written in a language we don't yet fully speak. Inside the collider, the subatomic world is a noisy, chaotic city. New possibilities flicker and vanish in trillionths of a second. Most anomalies, those tiny deviations from expectation, turn out to be illusions of statistics, patterns born from chance, like faces glimpsed in clouds. Physicists chase them with patience and humor. When you can't find your keys, one of them once said, "Make new keys and see what fits." In their case, the keys are hypothetical particles, supersymmetric cousins of known particles, hidden photons, or something even stranger. Each new theory is another key turned gently in the dark. So far, none have opened the door completely. Yet, the search has yielded wonders all the same. In 2012, the LHC confirmed the existence of the Higgs boson, a long-sought particle that explains how matter gains mass. But the Higgs may also whisper to the invisible. If dark matter exists, it might interact faintly with the Higgs field, a kind of handshake between the seen and unseen worlds. Physicists now look for the subtlest irregularities in how the Higgs behaves, searching for hairline cracks in the smooth wall of known physics. Each run of the collider, each fresh round of data, trims away more of the uncertainty. Whole categories of possible masses and interaction strengths have already been ruled out. The search is narrowing, not fading. It's like exploring a forest at night with a single flashlight. Every place you illuminate doesn't just show what's there, it shows you where not to look next time. And sometimes, in the process of looking for one thing, we stumble upon another. The collider's work has deepened our understanding of how matter organizes itself, how symmetry shapes the universe, and even what the quantum vacuum, the quiet background of existence, really is. The pursuit of dark matter has become more than a hunt. It's a compass. It keeps pointing us toward places where new physics may lie waiting. There's also a poetic resonance to this method. To use collisions, moments of pure violence, in search of something as silent and enduring as dark matter, is to see beauty in contrast. Each flash of energy at the LHC is a miniature creation story, an instant of chaos, followed by cooling, expansion, and perhaps the birth of something that will slip forever into the dark. The detectors that record these moments are layered like colossal onions, each shell tuned to catch a specific kind of signal light, charge, magnetic track. Together they form a portrait so detailed that even what's missing becomes visible. A gap in the data becomes a fingerprint. A silence becomes an answer. Even if the LHC never captures dark matter directly, it is paving the way for what comes next. Future colliders capable of even greater energies, probing deeper into the unknown. Perhaps the key lies just beyond our current reach, waiting for a slightly higher turn of the dial. The pursuit continues, not from frustration, but from fascination. Science, at its heart, is a long conversation with mystery, and dark matter remains one of its most eloquent partners. But not everyone is convinced that an invisible substance is the only solution to the universe's puzzles. For all the evidence pointing toward dark matter, some scientists have wondered if perhaps the problem lies elsewhere, not in what's missing, but in how we interpret what we see. Maybe the cosmos isn't hiding matter from us. Maybe gravity itself is playing by slightly different rules than we thought. This alternative view began to take shape in the early 1980 seconds, soon after Vera Rubin's groundbreaking measurements showed that galaxies spin too fast for their visible mass. Physicist Mordechai Milgram proposed that perhaps Newton's laws perfect within the solar system might need a gentle adjustment at the lowest accelerations, the kind found at the edges of galaxies. He called it modified Newtonian dynamics, or MOND. In MOND, gravity doesn't fade as quickly as Newton predicted. When accelerations become extremely small, the force weakens more slowly, providing just enough extra pull to keep a galaxy's outer stars from drifting away. With this simple tweak, MOND could reproduce the same flat rotation curves that led others to infer dark matter, but without adding any invisible mass at all. It was a bold idea, elegant in its simplicity. For many galaxies, it worked beautifully. MOND could predict stellar motions with uncanny accuracy, and naturally explained certain relationships that dark matter simulations sometimes struggled with, such as the Tully-Fisher relation, the precise link between a galaxy's mass and its rotation speed. It seemed to hint that perhaps the universe followed a deeper rule we had overlooked. But simplicity can be deceptive. When astronomers tested MOND on larger scales, clusters of galaxies, for instance, cracks appeared. The extra gravitational pull required to hold those clusters together was far greater than MOND could provide. Even with the modified equations, there wasn't enough gravity to explain the observations. To make the numbers work, MOND itself needed to introduce some additional, unseen mass. The irony wasn't lost on anyone. The theory designed to eliminate dark matter ended up asking for a little of it after all. And when MOND met the cosmic microwave background, the ancient afterglow of the Big Bang, its difficulties deepened. The delicate pattern of ripples in that primordial light matches perfectly with the predictions of the dark matter model but resists reproduction under MOND. It's as if MOND could describe the streets of a city perfectly, but struggled with the shape of the continent beneath them. Still, the idea refused to die. If Newton's laws might need adjusting, perhaps Einstein's theory of general relativity, our most complete understanding of gravity, might need a slight revision too. From that thought grew a family of theories known collectively as modified gravity, or sometimes MOG. These theories introduce subtle new fields or forces that alter how gravity behaves across great distances or in weak environments. Some versions even suggest that dark matter and dark energy, the two great unknowns of modern cosmology, might be different faces of the same deeper phenomenon. Modified gravity can mimic many of dark matter's effects. It can explain the motions of stars within galaxies and, in some cases, even replicate gravitational lensing, the bending of light by mass. For those drawn to elegant simplicity, these models are appealing. Why invent an entirely new form of matter if a small tweak to the existing laws could achieve the same results? But as the evidence accumulates, the cosmic scales seem to tip back toward dark matter. Simulations of the large-scale structure of the universe, the cosmic web of galaxies and voids, match reality only when dark matter is included. Modified gravity struggles to reproduce those same vast patterns. It can explain galaxies, perhaps, but not clusters, not the full choreography of cosmic evolution. It's like navigating a landscape with two maps, one detailed and complete, the other elegant but missing a few vital roads. Even so, Mund and its successors have earned enduring respect. They remind us that every idea, no matter how dominant, must remain open to challenge. Science lives on questions, not uncertainty. Modified gravity stands as a philosophical counterweight to the prevailing view, a gentle voice that whispers, "What if we've simply misunderstood gravity itself?" Some physicists even explore hybrid models, blending both approaches, a universe with dark matter, but also with subtle modifications to gravity's behavior. Perhaps the truth lies in between, in a harmony of matter and law. The cosmos has never been fond of giving us single answers. It prefers paradoxes that resolve only when we learn to listen more carefully. And so the search goes on, in the darkness below mountains, in the glow of distant galaxies, and in the bright collisions beneath Geneva. Whether the solution is a hidden particle, a new force, or a deeper rule of gravity, the question itself keeps us close to wonder. Somewhere between the equations and the silence, between light and shadow, the universe is still speaking. The universe rarely settles for simple answers. It prefers a kind of graceful contradiction, a both-and, rather than an either-or. Perhaps it's not a question of choosing between invisible matter and modified gravity, but of learning how both might contribute to the same cosmic story. For now, though, the balance of evidence leans strongly toward dark matter. Its traces run through the sky like a watermark. We see its fingerprints in the bending of light around galaxy clusters, in the quiet way galaxies hold themselves together, in the ancient ripples of the cosmic microwave background, in the patterns of structure that stretch from one horizon to the other. No single version of modified gravity has yet managed to reproduce all those clues at once. But that doesn't make the challenge a failure. It means the mystery is richer than we imagined. Every good alternative sharpens the main theory, forcing it to defend itself, to refine its assumptions, to question its own elegance. Even the ideas that don't survive the test of data help the others grow stronger. The conversation between possibilities, between unseen matter and unseen laws, keeps cosmology alive. One vision fills the universe with invisible substance, a dark scaffold that holds the visible in place. The other imagines a universe whose rules subtly shift with scale, where gravity itself bends differently across the grand distances. Both are ways of trying to make sense of the same clues, and both remind us that gravity, though deeply understood, may not yet be fully known. The truth, when it arrives, may borrow from each, a universe that tweaks its rules just enough to conceal something vast beneath the surface. Whatever form that truth takes, the search itself has transformed our view of existence. Every equation scribbled at midnight, every simulation humming in a computer cluster, every quiet argument over coffee in some mountain observatory adds another thread to the great tapestry of discovery. For now, dark matter remains the leading explanation, supported by evidence as deep as space itself. But science moves not on certainty, but on questions that resist it. In that resistance lies progress. Every detour, every dead end, illuminates the road ahead. When we step back and view the cosmos as a whole, a quietly astonishing picture emerges. Everything we've ever seen, every star, every galaxy, every cloud of gas, every breath of air, every human thought, makes up only about 5% of what exists. The shining galaxies scattered across the night, the delicate atoms composing oceans and skin and starlight, all of that luminous matter forms only the thinnest surface of reality. The rest, the vast unseen majority, is divided between two invisible dominions, roughly 27% dark matter and 68% dark energy. Together they fill the universe not with light, but with structure and motion. The cosmos is not bright with stars so much as it is sculpted by absence. Imagine standing inside a cathedral so enormous that its far walls vanish into darkness. The colored glass above you, the stars, the nebulae, the galaxies, are the glowing 5%. The arches and pillars that give the space its shape, the air that holds the sound of every echo, are the dark matter and dark energy. They don't shine, yet without them, the architecture would collapse. The beauty of the universe lies not only in its light, but in the dark scaffolding that allows the light to exist. Dark matter, that quiet cosmic glue, binds galaxies into clusters, holds stars in their paths, and draws vast filaments that connect galactic cities across unimaginable distances. Without it, the universe would have no skeleton, no form, only drifting fog. And beyond even that lies something stranger still: dark energy, the invisible breath of the cosmos, a pressure woven into the fabric of space that drives everything apart. It's not matter in any familiar sense. It doesn't clump or flow or collapse. It's a property of the vacuum itself, a gentle acceleration that makes the expansion of the universe speed up with time, as though space were slowly exhaling. Galaxies that were once bound by the pull of gravity now drift away faster and faster, carried by the tide of this invisible force. The numbers can sound abstract, 5, 27, 68, but together they tell a story of astonishing balance. The universe isn't an empty void with a few sparks of light. It's a woven fabric where darkness and brightness share the same loom. Even though we cannot yet grasp what dark matter and dark energy truly are, their presence is written across everything we can observe. The spin of galaxies, the lensing of light, the ripples frozen in the afterglow of the Big Bang, all of it speaks the same quiet language of the unseen. Yet this dominance of darkness doesn't make the cosmos bleak. It gives it depth, grace, and mystery. The atoms that build everything we touch, mountains, oceans, trees, and people, are the rare jewels of existence, glittering in an ocean of the unseen. We are, in a sense, creatures sculpted from the residue of light, carried through time by the invisible. There is comfort in that. The universe is vast, yes, but not indifferent. Its apparent emptiness is full of quiet purpose. The space between galaxies isn't a dead void. It's a stage where gravity and energy perform an ancient duet. For nearly 14 billion years, that duet has shaped every luminous trace we see. Even the word nothing feels too small for what fills space. The vacuum hums with energy. Fields and fluctuations shimmer in every cubic inch. Quantum particles flicker into existence and vanish again before we can notice them. Gravity curves this invisible sea. Light crosses it, and dark energy breathes through it. What we call empty space is, in truth, the most alive thing we know, the foundation from which all things rise. Astronomers sometimes describe the universe as a kind of inventory. If you were to make a pie chart of existence, only a thin slice would be labeled known. The rest would be covered in question marks. But those question marks aren't signs of failure. They are invitations. They remind us that ignorance in science isn't a void to be feared, but a map of where wonder lives. That we can measure these proportions so precisely even without knowing the ingredients is one of humanity's quiet triumphs. The story of dark matter and dark energy is proof that the unknown is not the enemy of understanding. It is its birthplace. Each mystery uncovered doesn't shrink the world, it deepens it. The more we learn about what the universe hides, the more miraculous it becomes that anything shines at all. Our understanding will continue to evolve. Future telescopes may trace the fingerprints of dark matter particles. New theories may finally name the energy that fills the vacuum. But for now, we live in an age of luminous uncertainty, knowing that almost everything that exists is invisible, and yet everything fits together in perfect, delicate balance. When you look up at the night sky, you're not just seeing stars, you're seeing the surface of an invisible ocean. The galaxies are lanterns floating on its tides, held in place by the pull of dark matter and carried outward by the breath of dark energy. It's easy to feel small in such a universe, but maybe that's the wrong direction of all. We are not insignificant specks lost in cosmic vastness. We are rare concentrations of visibility, the universe briefly aware of itself. The same forces that shaped galaxies have, through an unbroken chain of events, shaped eyes that can look back and wonder. The universe, through us, is contemplating its own dark reflection. So yes, most of everything is unseen, but within that unseen lies the architecture of all that is. The dark is not absence, it is foundation, not an ending, but a beginning. The unseen is the framework that makes light possible. As we drift toward tomorrow, under a sky that has watched for billions of years, the stars remind us of something subtle and profound. Light is precious because it is rare. Darkness, far from empty, is full of meaning. The universe, made mostly of nothing, is the greatest something there has ever been. Vast, silent, and softly alive with the promise of what remains to be understood. And the night sky we see tonight, beautiful as it is only a temporary arrangement, a single page in a book that continues to write itself across trillions of years. Stars flare and fade, galaxies collide and merge, clusters hold together, and still the story moves on. Even the brilliance of starlight is a passing phase. One day, when all the stars have exhausted their fuel, it will be the dark matter that endures invisible, patient, steady, preserving the faint outlines of the structures it once cradled. Dark matter is the quiet sculptor of cosmic architecture, and that architecture will outlive the light it shaped. Stars will die, galaxies will dim, but the halos of dark matter surrounding them will remain like ancient ruins, holding the memory of what once was. Slowly, gently, those halos will diffuse, as if the universe were exhaling the last breath of its brightness. Over unfathomable stretches of time, the expansion of space will continue. Dark energy will keep working, drawing galaxies farther apart. The clusters that remain bound by gravity will persist as lonely islands, while everything beyond them drifts out of sight. The night will deepen, not through collapse, but through distance. In that far future, the great blue stars will have burned out long ago. Only the small red ones will remain, glowing softly for trillions of years before finally cooling into black dwarfs, cold embers, floating in an ever-expanding void. The galaxies that once gleamed like jewels will become ghostly remnants, faint and solitary. Their dark matter halos will still exist, invisible as ever, shaping the emptiness, tracing the outlines of a cosmic web that no longer shines. Eventually, light from one cluster will never reach another. Each will become a solitary universe, adrift in silence. To any observer, if such a being could exist in that distant age, the cosmos would appear still and empty. Every other island of matter will have slipped beyond the horizon of visibility. And yet, even then, gravity will hold its shape. The dark matter will linger, its quiet weight preserving the skeleton of creation. The ancient filaments, the invisible bridges between galaxies, will persist as faint memories of connection. Even black holes will fade, releasing their energy as the softest whispers of radiation. What remains will be the dark itself, endless, diffuse, and serene. It's a vision that feels peaceful rather than tragic. There's no final explosion, no abrupt erasure, only a slow, graceful fading. The universe doesn't die, it rests. It returns to the stillness that was always its home. In that silence, the forces that began it all, gravity, energy, the quantum tremor beneath existence will still be there. They will continue to hold the memory of light, patient and unchanging. The story of brightness may end, but the story of structure endures. The universe will go on being, even when there's nothing left to see. And perhaps that, in its own way, is the most comforting truth of all, that even in the deep future, after the last light has faded, the dark will remain faithful, still carrying the shape of everything that ever was. We live in the bright middle pages of the universe's book, a brief, golden interval when galaxies still gleam and the night sky still shimmers with stars. It's a temporary grace, a luminous chapter between long epochs of darkness. Billions of years from now, those lights will dim, their songs fading one by one, but the underlying shape, the quiet geometry of dark matter will remain. It will preserve the memory of everything that once was, like fossilized starlight in the bones of space. From a cosmic perspective, the future is not a thing to dread. It's the natural continuation of what has always been, creation and dissolution, brightness and shadow trading places in perfect rhythm. The same physics that allowed galaxies to bloom will one day allow them to rest. In that fading, there's no tragedy. There's peace, a long, slow return to balance as the universe lets go of its brilliance and settles into its enduring form. We've been taught to think of darkness as absence, but in the cosmos, it is the opposite. The dark inherits everything. It is the keeper of structure, the custodian of memory. When the last photon has crossed its final path, when the final star grows cold, the universe will still be here, vast, quiet, and patient beyond imagining. And perhaps, just as the stars once rose from darkness, something else might rise again in a form we cannot yet imagine. The universe is nothing if not creative. Its silences may not be endings, but pauses a deep breath between movements in a cosmic symphony. For now, though, we live in the era of light, when galaxies still glow, when the Milky Way still paints its river across the night, when we can still look up and ask what will come after. The fate of the dark is not a tragedy, it's a continuation, the long echo of creation itself. The islands of night will drift apart across their silent sea, each one carrying the memory of light. And though the far future belongs to darkness, this fleeting present, this shimmering age of stars, belongs to us. Darkness has long carried a reputation for fear and absence. Yet, when you look closely at the universe, you find that darkness is not the enemy of light, but its foundation. Every star, every galaxy, every glint of brilliance exists because the dark made room for it. The invisible doesn't hide the cosmos, it holds it together. If you imagine the universe as a vast tapestry, light is only the embroidery, delicate threads of gold tracing across a deeper weave. The true fabric, the loom itself, is dark matter. Across its invisible strands, galaxies are strung like beads, their patterns guided by gravity's silent hand. In that quiet strength, the cosmos found its form. Darkness is not absence, it is structure. The story of the universe has never been a battle between light and dark, but a partnership. From the first moments after the Big Bang, darkness shaped the stage so that light could play its brief and brilliant part. The stars are notes in a symphony written mostly in a quiet key. Without the unseen matter surrounding them, their music would never have begun. It's humbling to realize that beauty does not depend on visibility. The glowing spirals of galaxies are breathtaking, not because they stand alone, but because they reveal what the darkness can do. Every swirl of starlight is a sculpture carved by gravity's invisible hand, a quiet art form practiced for billions of years. The medium is mystery. The masterpiece is motion itself. And yet the mystery doesn't frustrate, it soothes. There's something deeply peaceful in knowing that not everything must be illuminated to be real. The unseen doesn't demand explanation. It simply exists, steady and patient. It invites curiosity without urgency, like a lake, reflecting both day and night without preferring either. We forget, sometimes, that light owes its meaning to darkness. A sunrise is beautiful, not because it ends the night, but because it emerges from it. The blackness between stars gives their shimmer its depth, gives their presence its wonder. Without contrast, there would be no awe, only endless brightness, blinding and flat. Dark matter reminds us that most of reality hums beneath perception. The universe is not a blaze, but a hush. Galaxies drift, clusters turn with slow grace, and immense voids stretch between them, perfectly still. The dark doesn't rush. It has no need. It simply is. And within that stillness lies a kind of cosmic grace. To study the unseen is not to try to conquer it, but to listen. Every experiment, every telescope, every carefully tuned detector is a small act of reverence, a quiet bow toward the unknown. Scientists do not chase mystery out of dissatisfaction, but out of gratitude. Gratitude for a universe generous enough to still surprise us. Perhaps that's the real lesson of the dark. Not everything must be known to be meaningful. The cosmos is under no obligation to reveal all its workings. It gives us glimpses aglow here, a whisper there enough to keep our wonder alive. Our curiosity is a lantern we carry through its corridors, lighting only a few steps at a time. To live in a universe made mostly of unseen matter is to live in a place where imagination and science intertwine. We cannot touch dark matter or see it directly, yet we feel its influence everywhere. in the spin of galaxies, in the motion of clusters, in the fact that we exist at all. It is the invisible presence that connects everything, the gravity that reminds us that nothing stands alone. There's poetry in that connection. The atoms in our bodies were forged in the hearts of stars, but those stars were born within halos of dark matter. We are, in the truest sense, children of both light and dark. Our atoms once burned brightly, but their paths were shaped by something silent and unseen. To gaze at the night sky is, in a way, to look into a mirror, the visible and the invisible, working together to make the whole. Every spark of light tells a story of fire and fusion, but the space between those sparks tells an older story, one of patience, of gravity, of form. The stars are where they are because the dark guided them. Perhaps the most beautiful thing about the unseen universe is its serenity. It doesn't compete with light, it welcomes it. Galaxies move as though in slow meditation, following paths traced long before the first photon was born. The darkness doesn't ask to be noticed, but once you sense it, you begin to feel it everywhere, not as emptiness, but as rhythm, as balance, as breath. And maybe that's why the study of dark matter feels so strangely comforting. It tells us that mystery is not the opposite of knowledge, but its companion. The unknown isn't a wall, it's a horizon, one that always moves just far enough ahead to keep us walking. Even when the universe doesn't answer immediately, the act of listening becomes its own kind of discovery. The more we learn about what we can't see, the more we realize that we are participants in it. We exist because of it. The same dark scaffolding that shaped galaxies shaped the conditions for life, for thought, for wonder, for the very act of asking. We are small, yes, but our smallness has meaning. We are the kind of small that can hold the vast within awareness. So let the darkness be a comfort. Let it be the cradle that holds the stars, the loom that weaves the galaxies, the silence that gives the music its shape. In a universe where most of what exists is invisible, our awareness itself becomes a form of light, not to chase the dark away, but to honor it. The unseen is not a void to fear, but a landscape to marvel at, an infinite field of possibility, stretching beyond sight and time. The night sky reminds us that the universe need not be fully known to be profoundly beautiful. Some truths live best in shadow, waiting not to be solved, but to be felt. And as you lie beneath that same sky tonight, know that you are surrounded by the quiet beauty of the unseen. Most of the universe is invisible, and yet it holds everything we love. We've drifted through that hidden framework tonight, the dark lattice that steadies galaxies, cradles stars, and gives the night its architecture. We began by wondering what keeps the cosmic lanterns from drifting apart, and found the answer not in light, but in gravity's soft handwriting. We followed its traces through clusters, through the web of galaxies, through the earliest glow of creation, and the picture that emerged was simple and tender. The brightness we adore is embroidery. The fabric beneath is dark. Close your eyes for a moment. Picture a single lantern suspended inside a clear glass sphere. The glow is the stars, the nebulae, the long river of the Milky Way. But it is the unseen sphere that holds the lantern steady. That is the universe we live in. Light singing because something silent keeps the rhythm. The darkness is not an enemy to banish. It is a cradle, a patient architecture, a loom of night weaving galaxies of light. And there is comfort in that. It means we don't have to know everything to feel at home here. The unknown can be a soft place to rest, a reminder that curiosity is not a burden, but a companion. When the equations fade and the graphs fall quiet, the sky still offers its gentle truth, a balance of brightness and shadow, each giving the other meaning. If this long drift through the cosmos brought you a little calm, taught you something new, or simply kept you company as the day exhaled, you might help this small corner of quiet science reach others who could use it too. A like, a subscribe, or a share whispered into the algorithmic dark. No rush, no pressure, only if it feels right. Now let the questions settle like dust in a sunbeam. Let the room grow still. Outside, the stars keep their slow promises, and the spaces between them hold steady. You are part of that balance, a brief light carried by a greater quiet. Thank you for spending your evening with the sleepy scientist. May your night be easy, your dreams unhurried, and your rest deep. Until next time, sleep well beneath the stars.